happy to restart and have professor here at RPI, Yungfeng Shi, who is from the Department of Material Science and Engineering. We have a lot of close relations with this department here in physics. We have a number of people that collaborate with material science and engineering. And he's going to talk to you about one of the important sorts of modelings that you can do using computers of physical systems and molecular dynamics. So.
Great. Welcome everyone to Rensselaer. Raise your hand. How many are your undergrads? Okay. The rest are graduate students, and I assume everybody is physics background, right? It's all in. I'm sorry. Chemistry. Excellent. So, chemist, material scientist, rest is physicists. Great. So today we're gonna have this 3-hour crash course on molecular dynamics, right? I hope it is fun. I hope it's useful. So we are not only going to teach you the sort of 1,000 miles overview of the MD, but you also gonna have some hands-on activity which you can play in your computer. Before we dive to MD, I do want to make a little bit of connection between material science and physics, right? So for those, anybody heard about material science? All right, great. The best analogy, right? My best analog of a material scientist is this chef, right? This chef. Why? Because the chef takes the raw material, process it, and then it has this better property, and then it use it, right? So this is how material scientists do processing, get the structure, and then understand the property. This is the trinity, holy trinity of material science, right? Structure, property, relationship. When we talk about structure-property relationship, this is essentially condensed matter physics, right? So you will see so many physicists are in the material science department. I can count 1/3 of our department are physics PhDs. The other way works too. We do have one material scientist who is also in the physics faculty. Professor Goqing Wang used to be the department head here, right? So there are so many connections. And if you look at any engineering school, material science and engineering is probably the only department has science in it, okay? So we care a lot about the science, aka physics and chemistry, right? All right. Okay, so just to sort of give you a little bit of a flavor of material science, at the same time, think about material science for your next, move. It's very fun. I will give you like quick 3 examples of why material science is basically recognized in physics field, right? So 1920s, the Nobel Prize in Physics was awarded to Guillaume. You probably have a better pronunciation. Guillaume, okay. for discover this very special material called INVAR, iron nickel alloy. What is special about this particular alloy? This alloy has extremely low thermal expansion coefficient. Right? So what does that mean? When you heat up a material, usually material will expand. This is called positive thermal expansion coefficient. Some materials are very weird. If you heat it up, it can shrink. Negative thermal expansion coefficient. INVAR, almost 0. You can see this at this particular composition. It's almost 0. Right? Use INVAR, you can make the world's best, most accurate clock at that time, more than 100 years ago. It's used until 1930s, other timekeeping techniques start to pick up, and use in a lot of high precision instrument. That's why it is worthy the Nobel Prize, right? However, to understand this very anomalous thermal expansion coefficient, you have to go back to very quantum mechanics, magnetism, to understand that, right? Second example, high temperature superconductor. Second Nobel Prize in physics awarded to a material discovery, right? This totally bizarre, unheard of. How come you can get superconductor out of oxide, right? Right? This totally, and the third material example, of course, graphene, right? It generates probably the biggest buzz, but no application, great application yet, right? So this is the third. So in the to sort of give you an example, the complexity in the field of material science, how how this very almost the concept that make material science a separate discipline. This concept is called dislocation. Anybody heard about the concept of dislocation? All right. So this particular concept really makes material science to stand out as a separate discipline, not just a very tiny branch of condensed matter physics. What is a dislocation? This is I should have a animation here. Okay, I don't, but you will be able to play with it, right? So essentially, this is a one-dimensional defect, right? Can you see this, right? So at the time, you don't even have the microscopy or any technique to see atoms. Mathematicians and physicists already conceived the concept of dislocation, right? Then they use this concept of dislocation to explain the macroscopic plasticity, right? So Vito Volterra was and Arawan, Taylor, and Paleni, they conceived the concept of dislocation. And then finally, this is the transmission TEM, transmission electron microscopy, finally be able to observe this, right? So physicists actually and mathematicians actually, be able to predict it before it was observed, right? So why in the field of material science we want to use computational method as a, and you can see, that's why you guys are all here, right? You want to study computations, all kinds of different computational methods. The overwhelming reason is in this graph. Conventional technology, any conventional technology, you kind of grow, right? And then you reach a plateau, right? And then there's a sudden, technology innovation. You increase again, and then you saturate, right? You can see the amount of, maybe cars you produce, right? The total amount of powers, we produce. It's all like this. It's saturate. What is not? What is not is computational power. It is governed by the so-called Moore's law, right? Moore's law. Every 18 months, the computational power gonna double, and the cost gonna half, right? So all the way to today, this trend keeps, right? So that's why computation becomes cheaper and cheaper. No other human civilization sort of capability rivals this. Nothing else. That's why, I talked to a chemist, really, big guy in the field. He's an experimentalist, and he told me this like 10 years ago when I was a postdoc, and he said, you know what? I imagine 50 years from now, he's working on explosives. Okay, at that time I'm modeling some explosives. So, and he said, I can imagine 50 years from now on, maybe 90% of the researchers gonna do computation, maybe 10% gonna do real experiments, because experiments are so dangerous. Make sense? And the computational power, the accuracy afford to do that. Think about in the case of weapon design and so on, right? So 99% is all computation, and maybe 1% you validate, right? So this model will propagate to all field. So you guys are right to study computation, right? Right? So this is just a fun thing to look at in the past 30, 40 years, the evolution of Mac, right? Give you another material science example, right? So this particular example is a very interesting nano tension test. So this is done in TEM. You're pulling a little sort of cylinder of a material called metallic glass, right? And using the fastest video camera, right, with the highest frame rate, and the two frame you have is essentially, one is this, the other is this. Really, really brittle failure, right? I know every one of you, as a physicist, you have a heart to understand, right? You want to understand what's going on in between. Make sense, right? I do too, right? So, what we can do in computations is to understand what happens in between. But also, we want to zoom in at the atomic level to understand the deformation mechanism, right? So molecular level simulation, particularly MD simulations, has the capability of answering part of the question, not the whole question yet. But in certain situations, you can answer the, pretty much, cover the time scale as well. Also, more importantly, you will be able to address the other important question is, what happens if the condition varies, right? You will see that experiments becomes more and more expensive, so that maybe I can use computation to change the temperature, change the loading rate, right? Change the composition, right? So that I can save a few $1,000. Make sense, right? So this is really, really important. Now, I do want to say one thing. In MD simulations, at least for me, my goal is not to simulate the reality. Okay, I do not want to just simulate the reality, because the reality is already there. Make sense, right? I want to simulate a system so that I can understand. How do I do that? I want to make a simpler system that still produces the most robust phenomena, exactly the same as the experiments. Now I can understand, right? So I want to simplify the reality to a state that still produces the same phenomena. Now that is understanding. I do not want to just simulate the reality. For instance, I don't know, 100 years later, right? I could probably simulate 100, maybe 1,000 gold atoms, right? For 1 second, right? I could probably do that, but I will never do that because it gives me nothing. Make sense, right? But if I see, let's say, if I say heating up the gold, right? It melt at a certain temperature, right? Oh, I see melting. If I use a way more simpler potential, let's say a Lindner-Jones potential, right? I see a FCC, it melt, give me almost the same phenomena. Aha, I can understand gold just by Lindner-Jones. Make sense? That gives me understanding, right? I want you to understand I'm in the camp of to use the minimum model to describe the system, not to make it as accurate as possible, okay? Right? So here is kind of a sort of the overview of what this modeler, MD modeler will do. The objective of the MD modeler is to recreate the physical system, but in a minimalist way, right? In a minimalist way. And what he will do, first, he will translate the materials system into mathematical forms, or we'll discuss exactly how we're going to do that. Then, this is this is probably more important, is to identify and do the analysis to understand this process. Most people spend, I don't know, 90%, right? Just run the simulation, right? Just run the simulation. Okay, done with it. And this low-level MD papers basically shows some snapshots, right? That is, I think is not do MD right? You're gonna have to do the right analysis. So the analysis, usually I will count for 1/3 of my research time, right? 1/3 of time you have to do analysis. 1/3 time setting up the system, running it, and then the other 1/3 writing the paper. That's roughly, you have to write, right? All right. Now, let's put MD simulation among other simulation methods. What simulation method you have covered? You have covered DFT, right? By Professor Shankar, Sandra Raman? No? The DFT, okay. DFT not yet, okay. Oh, okay, the continuum part, okay. Right, so,
Vincent will talk about DFT.
I see. Gotcha. So at the electronic level, you are essentially dealing with Schrödinger's equations or Quantum equivalent. At the atomic level, you are dealing with Newton's law, Newtonian equations of motion. Right? Continuum level, you're dealing with, for instance, this heat transfer type of model that is the fixed heat transfer law, right? So you are dealing with certain equations. I want to sort of use Angry Bird, right? Anyone not playing Angry Bird before? No, you should try it, right? So in Angry Bird, right? So Angry Bird is a perfect example how MD works, right? So in this app, the program has to determine where the birds are. Make sense? Position of the bird and the velocity of the birds. Also the force on the bird. The bird is about to crash on a board, or the bird is on the slingshot at a particular position, right? The force. Also gravity. Make sense? Also gravity. So you calculate all the force, you divide it by the bird's mass, you get the acceleration, right? Position, velocity, acceleration, you can integrate for the next step 1/30th of a second position of that bird, right? You do that for all the birds. You do it 1/30th of a second, you do another, now you have the full game, right? So basically, MD simulation is essentially, you not only have, one type of bird, you have many, and they behave in a, sometimes complicated fashion described by force field. So this is MD. This is MD. If you ever played with Angry Bird or played pool before, you understand, right? You will understand. So that's all for MD. We're done, right? Of course not, right? So okay, let me use a better version, right? Now you have the position, you have the force, you have the position, you have the force. Basically, the force will be calculated from the potential energy, right? So the potential energy is derivative with respect to the position of that particular atom. Negative, that gives you the force, right? So how to write the potential energy is very complicated, right? We're gonna spend quite a few slides on that, right? So once you know the force, you will be able to calculate the acceleration, and you just integrate it again and again. There's a very important concept. Is time step. This is the delta t. This is a 1/30th of a second in your iPhone, right? In the app. If this is very, very small, you don't go very far. Make sense? Right? The computation is very inefficient. Make sense? Right? But if delta t is very large, your integration will not be stable. Make sense? So usually, the rule of thumb is 5% of your vibration period. 5% of your vibration period. Okay, you're gonna see some examples when you do the hands-on. You can actually, I would welcome you to, when you do hands-ons, make the time step really large. See what happens. Okay, I want you to try that, right? Basically, what we do usually is that we want to make it as large as possible so that the integration is still stable, right? Right? So we don't want to be on the safe side. We want to cover as long as possible so that, the simulation runs shorter, right? What can we write about the potential energy? The potential energy is a function of all the atoms. The easiest way to write this is assuming the interaction is only binary, only pairwise. That means if I'm pretty close to him, right? So our force, the force between us, the potential energy contribution to the total energy has nothing to do with you, right? You can be in between us. It will not shake us our, bond. Make sense, right? That's pair interaction, right? Pair interaction. The easiest pair, absolutely not the easiest. There's hard sphere, but there's of course, right? There are easier force. So this force field is a very popular force field called Lennard-Jones. Force field has two parameters. One is epsilon. It tells you the depth of the potential, essentially the bonding strength of the potential, and sigma. Sigma, basically, you can think of the size or the range of the interaction for not precisely, almost the equilibrium bound distance. Okay, there is a factor in front of it. Now, this is named after Sir John Edward Lennard-Jones. So this is one person, right, Lennard-Jones, and he was awarded the Nobel Prize for sort of not inventing this form, but to understand non-ideal gas equation of state, right? Very, very famous guy. All right. Now we're going to the nitty-gritty of MD now, right? So let's say I can use this computer, right, to simulate 1,000 atoms, maybe 1 million, right? 1 million atom. 1 million atom, how big it is? Anybody knows? For iron. How if I put in a cube, how big that would be?
Are we assuming there's space in those case?
Oh, I would just it's like a single crystal iron, 1 million atom. How big? Microns? 10 nanometers. That will be microns. You go to billions. Right? So think about it. Even 1 billion atom, you only go 1 micron, right? So that there is a significant size effect, right? Significant size effect. I don't want size effect. Also, I don't want surface. Make sense? Right? So what is the number one trick we have to eliminate surface and eliminate size? We want to study bulk effect. We want to study the behaviors of iron. How do I do that? There is a very important trick we play called periodic boundary condition. Periodic boundary condition. So this is not an isolated system. This is not vacuum. This is not vacuum. How do we do it? We basically create a periodic boundary condition. That means this side will be itself. This side will be itself. Up, down, in all direction. Make sense? So there is no surface, right? Very smart idea. Now comes a very important point. Yes?
You wouldn't run into size effects though, because you have a small box and a lot of atoms, you're getting more dense.
What do you mean more dense? I can use the same density, right? If I want to study iron, I would use the same.
You have to have some, you have to effectively, even if you're using periodic boundaries, like you're setting some size the system you have.
No. This is my system. This is my 1 million atom system. Right? So basically, the key here is that when this atom is pretty close to the boundary, right? This atom is not seeing vacuum here. It sees this atom. Make sense?
Yeah.
Right? That's the key.
Yeah. No, I get that. But
Yep.
I'm saying like
It goes infinite.
I think Eric means there's effective long distance interactions.
yeah, like
Of course. Okay, I get your point. So all these, when you have really long-range interactions, for instance, Coulombic interaction, there are other tricks to deal with. So here we just think about short-range interaction. So far away, we don't feel a force. Make sense? Mm-hmm. Yep, that's a good point. Right. Now, there's a very important point is that, for instance, right, this atom and this atom, they looks like their distance is this big, but because this atom sees the image of this atom right here, so this is the real distance, okay? So once you have pure boundary condition, when you calculate the distance between two atoms, be very careful. You're gonna select the one that is the closest. Make sense? Right? This is very, very important, right? The real distance between atoms. All right, trick number 2. Think of, yes?
So why do you choose it to be the shortest distance?
Right, so basically, let's say you are running some kind of, let's say I want to do a very simple analysis, right? A very simple analysis. This analysis is calculate how many neighbors do I have, okay? So basically this is also a short-range analysis, if you will, right? Right? Now, what I do, the simplest is, okay, I'm gonna loop from 1 to 1 million atom, and then I'm gonna look at all the other million atom to see whether they are within a certain cutoff distance that I call it a neighbor. Make sense? Right? Now, when I do this double loop, I will have to choose. You will have the situation of this. Make sense? I'm not gonna count that because I only interested in the short-ranged, essentially analysis or interaction. Now, having said that, we are not forgetting this interaction. This interaction is still there. If it is a long range, like a Coulombic interaction, that interaction is still there. We are not killing it. But what I'm saying is that when you calculate these short-range potential or analysis, you only care about short range. You only select the shortest. Right? Yes, good point. All right.
So can I ask you a question?
Yeah.
So when you're using, say, the linear
Uh-huh.
potential, and you have to look at all these pairs,
Yes.
you put some kind of cutoff where
Yes.
you don't look at pairs beyond a certain
No.
distance.
Yes. Yes.
So exactly this computation that you just described, you have to do it.
You have to, yes. So these are the very important tricks we play to speed it up. Yep. Right. Okay. Here. So here, what is the first trick? The force calculation is the most expensive calculation of MD simulation. So we have to speed up the force calculation, right? How to speed up the force calculation? I just mentioned that, right? You can calculate basically, around this room, everyone is an atom, right? So we have to calculate, right? From me to you, this is a pair interaction, right? Another pair, right? Right? And then from you to everybody, so on and so forth, right? So now let's just look at one atom, right? Just look at one atom. If I want to calculate the pair interaction involving this atom, I could include all the atoms, right? I could include all the atoms. Or I could play a trick that, okay, I don't really care the atoms too far away. How do I know? It's because, for instance, the linear zone's potential is, goes to zero pretty quickly, right? About, 2.5 sigma, away, it's like, 2%, right? Something like that. So I can safely ignore them, right? So now, instead of looking at all the other atoms, I'm only drawing a circle. Drawing a circle. Within them, I call it my neighbors. I put them in memories. This is my neighbor list. Okay, this is a very important trick. So next time I calculate the force, I only need to look at those neighbors, right? This is called the Verlet neighbor list. There is a better trick. I should not just draw the circle of exactly where the potential energy goes to zero. Make sense? I should give it a little buffer room. Why? It's because the atoms could move in and out. Make sense? Right? I will give it a little buffer so that, oh, I see them move in. I already have you. Right? And checking atom going in and out is a order n operation. Very cheap. Make sense? When we check atoms' motion, I just loop everybody to see, did you move more than, I don't know, 0.1 angstrom, right? This is a very cheap operation, right? So now, basically, this is called the skin layer. This is called the skin layer. For instance, in low temperature, if you are modeling a crystal, you can put the skin layer as small as possible because atoms are not moving that much, right? So you can, you basically hold a little bit of atom and you're fine. But at high temperature, the skin layer should be a little large because atoms are in and out, right? At the same time, when you hold a thicker skin layer, the overall number of neighbors you're holding a little bit more. Make sense? So there is a trade-off there as well, right? So this is neighbor list. Yes?
Is that like the atoms are just moving, right?
Yes.
So, you said like you have to select the closest distance for each atom.
Yes.
So is that possible? Like, since the atom is moving, so the closest distance is also
changed. So usually the simulation box is way larger than the cutoff. So it's not going to be, oh, this image just moved out, the other image moves in. Not going to happen. So simulation box is usually way larger than the cutoff. Yep. All right. Let's look at the second trick. This trick is called link cell, right? So far we know we have to build this neighbor list, right? Using the neighbor list, it will speed up the calculation so that I can only calculate the force from within the neighbor list. How do we build the neighbor list? How do we build the neighbor list? Here is a very, very smart way to do it. This is called link cell. Let's see the obvious way. It's the double loop, right? I can loop over all the atoms, right? And then, for me, I loop everybody, right? So this is an n square operation. Make sense? This is an n square operation. You have 10 atoms, you will loop n square 100 times. You have 1,000,000, you got 10 to the 12th loops. Make sense, right? So it's a very expensive calculation. Instead, what you can do is this. First, we are going to create a grid or a cell, right? Like this. Then we're going to put all the atoms inside those cells. The cell size are larger than the cutoff. This is very important. The cell size are larger than the cutoff. Now, if I want to find, let's say, this atom's neighbor, right? Now my task is to find this atom's neighbor. What I can do is, first thing, I will find which cell this atom is contained in. Then I know this cell has boom, 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 8 neighbor cells. Make sense? I can go into each cell to dig out what are the atoms belong to that cell. So I have way less atoms to deal with. Make sense? This is an order n calculation. So using link cell, you will speed up your calculation tremendously, especially if you're dealing with billions of atoms. Right? This is a really, really important algorithm. I hope, Maybe, I don't think you're going to reinvent MD simulation, but you maybe use it in other situations, right? Makes sense? This is a really interesting technique, right? I hope everybody sort of get the gist of it, right? Right?
Why do we have the potential diagram?
So here's the potential. Why we have the potential? This is because we are dealing with short-ranged interactions, and essentially the range of the interaction, we call it cutoff, determines the size of the link cell, right? Imagine, okay, I want to use a cell as small as possible. Make sense? Right? I want to use a cell as small as possible, but you cannot. You have to be bigger than the cutoff. Otherwise, you will not get all the neighbors, right? So that is the trade-off. So that's why you always need to think about the force field. Yep, good question, very good question. All right. Okay. This is another algorithm, very, very important. I told you about the Moore law, right? Moore's law. It tells you the computational speed increases over time in power law, right? In the past 20 years, do you feel the computer speed increases much? A little bit, right? So the computational speed in the past 20 years mostly is through the algorithm called parallel, right? So essentially you just use way more CPUs to dealing with the same problem. Make sense, right? So parallel computing is extremely important. MD simulation is native to parallelization, right? So the most useful algorithm is called the spatial decomposition. So what is spatial decomposition? Spatial decomposition, yes, go ahead.
I'm sorry, you did finish this. I have a question regarding the previous.
Oh, go, say it first.
I was wondering why the time complexity was n. And
okay, right, good point. So here, right? So why this order is the order of n, right? Think about the few steps. Number one, you throw atoms into cell. You loop over all the atoms. You interrogate what is the position of the atom, right? You divide by essentially the position divided by, position minus the boundary of the box divided by the cell size. You do a floor. You get the ID of the cell. Make sense? Right? So this is absolutely order n operation, right? Right? Then number two, what do? You find an atom, you find the cell, you already know the cell ID, right? From cell ID, and you loop over the neighbor of the cell, right? For 2D, right? 8 neighbors, plus yourself. In 3D, 27 in total. And loop in every single one of them the number of atoms it contains.
So on average, number of atoms in each cell will be n, and if the total number of atoms is n and the number of cells is m, it will be n by m, right? On average, because that's since the position of the atoms are random.
Sure.
Yeah, so it should still be n.
No. Because this is only 27. I'm only looping over 27 cells, no matter how big the total system is. So it is 27 times the number of atoms in each cell.
The question is that m doesn't scale with your system size. So the first loop scale with your system size, but the second doesn't scale with your system size.
So yeah, so that's the order n. Yeah. All right, good question. Any time, right? So some of the algorithm is a little bit tricky to understand at the beginning. All right, so this is a spatial decomposition algorithm. How it works is that I will have, for instance, 16 CPUs. Okay, I'm going to divide the job, right? Divide the job among the 16 of them, right? The 16 of them. Maybe. Yeah, this is not a very big classroom. I usually, when I lecture, I usually want the students to come over to be CPUs or atoms. You guys want to do that or not? It's a
Sure.
Okay. So I want 16 of you, 4 by 4, and you will understand this idea way better. So think about your CPU. Yes. I know you guys in total is 30 or something, right? So you have them. So 4 by 4, please. Yes. So see, with pure bonding condition, everybody will have the same number of neighbors, right? So it's okay. Yeah, you can all face forward. What's that? A few more people. Come on. Yes. 4 more. Come on. Yeah, maybe. Yeah, we'll just move it over. Yes. Oh, thanks. Perfect. All right, great. Yes, forward a little bit. Okay, excellent. 16 CPUs, right? Think about, let's say if I have 1 billion of atom, each one of you gonna hold 1 billion, roughly 1 billion over 16 number of atoms, right? Knowing those atom information, are you all set? Are you all set?
No.
No. Why?
Because I know where like 1/16 of them are, I don't know where the other.
Yes. So you need to know a little bit more, right? That is called the ghost atom, right over here. So you need to know a little bit of your neighbor. Make sense, right? So you need those position information, but you don't update them. The atoms you own.
Yeah, don't do that. I'm not a CPU.
The atoms you own, you're gonna update them using Newtonian equation of motion. Make sense? You're gonna update them, the new position and so on. But you're gonna take your neighbor's atoms, right? Your neighbor means, who's your neighbor? You too. Yes, you too. Because see here. Make sense, right? And also, who else? You three. Yes. Yeah. Very good. Very good. All right. Now let's think about the messaging, right? You're gonna pass information because let's say after one time step, everybody already updated their information. They want to share, right? They want to share. How do they do it, right? How do they do it? So the spatial decomposition actually use an algorithm, very smart, 3 steps. You did it. You share all the information. How to do it first? Let's say, okay, these 3 steps in 3D, right? We have a 2D grid. First thing, you're gonna share the information with your, lateral, this direction's neighbor, right? For instance, right? What's your name? Sorry. Eric and Todd. So Eric and Todd, what they have is that Eric gonna share this information to Todd. Todd gonna share this information with Eric. Make sense? So you guys have the skin, is layer or ghost atom between you, fine. Not only that, you're gonna share with you. You're gonna share with you. You're gonna share with him. You're gonna also share, not yet, right? We're gonna do the lateral first. Don't jump the gun. You're gonna also share, yes, right? Remember that. Okay, second step, what we're gonna do is this. All right, now we're gonna do this way. Remember, this way is a little bit different, because you're gonna share a little bit more now. Because now this CPU already know the precise, the updated ones of this corner. Now I'm gonna share it. Make sense? So although Eric, what's your name? Carlos. So Eric never talked to Carlos directly. He passed on the information through Todd. Make sense? Right? Now you can imagine the other way. So 2 steps, you can do it. This is spatial decomposition. Okay, very good. Let's give them a round of applause. Oh, thank you. Great, thank you. Great, really appreciate your participation. Okay, you first.
So in this way, you can probably like share information about variables, right? But when you have
No, the sharing part is only the atomic position.
so you only share positions, no forces.
No force, because once I have the position, I can calculate. Each CPU is smart. They can calculate the force themselves. Make sense? Right? They have all the parameters. Everybody can calculate the force once they know the position.
What about something like electrostatic forces? Because those can be fairly long range.
Yes. So for electrostatic Coulombic interactions, we're going to calculate in reciprocal space. In reciprocal space, it is short-ranged. So there are techniques to do that. Yes. Yes.
Well, yes, I would agree that using all these CPUs is going to speed up the process. You're going to run into a communication bottleneck.
Absolutely. Absolutely.
I don't mean to get too deep into the hardware question.
Yeah. So usually what we do is that if you run any parallel jobs, you have to check the parallel efficiency, right? Basically, how much speed up I can obtain using so many CPUs, as opposed to I just run on one CPU. So a parallel efficiency, 50%, 90% is excellent. That means if I use 10 CPU, I got 9 speed up. Make sense, right? That was excellent. So usually you got, 50%, 30%, sometimes it's okay. Because, for instance, the blue jeans in RPI, you can regularly use thousands of CPUs. 30%, you still got 300 times speed up. Why not, right? So you check, and then you decide whether it's worth it. Sometimes you're absolutely right. If the atoms each CPU hold is too little, right? Then you will run into the problem of communication becomes too costly. The ghost atoms become, half of your atom, right? Then it's not worth it, right? So if you, double the amount of CPU, maybe slow you down sometimes, right? So you have to check, right? Last word on parallel is this. For MD, the parallel is always spatially. You can actually do it on atoms too, right? Not spatial decomposition. But never parallel can be done in the time domain, all right? If any of you figure out a smart way to parallel in the time domain, that could, I would say, even Nobel Prize worthy effort. That it is that, is that big, right? So think about, forget about, physics and chemistry and material science for now, biology, right? Drug delivery, docking of these biomolecules, protein folding, those requires seconds, milliseconds at least, right? If you were able to have atomic level dynamics, Newtonian dynamics, and you run for 1 second, even a small system, that's huge. That's huge. Okay, just think about that, right? Okay, so what we can get from MD simulation, we know all the position of the atom, velocity of the atom, force of the atom. We can calculate the temperature. Very simple. We know the kinetic energy, the velocity, then we will able to calculate the temperature. Also, we can calculate the pressure using the virial theorem. Not only the pressure, but the full tensor of stress. Not only the global value, the stress of the whole system, but also the local stress as well. This is very important for material science. For instance, a crack propagation, when you have crack tip, stress is way higher than the parts, right? All right, quiz time. You guys all had StatMac, right? I'm sorry? You answer the next question. All right, we'll see, right? So, you know, having lectures in the summer is already hard, I know. All right, now the common ensembles, right? NVE, we call it micro-canonical ensemble. Anybody knows what is a characteristic state function for that? So NVE, micro-canonical ensemble. Yeah?
It's a system embedded environment, and for this system you have constraint. I think for micro-canonical, right?
Yes, micro-canonical.
It should have the constant energy and the constant, I think the entropy, right? And without any
No.
energy exchange with the environment.
Yes, it doesn't exchange, but the entropy can change.
Yes, entropy itself can change.
Yeah. So what is a characteristic thermodynamic function? It is the entropy. Very good, very good. Usually we say negative entropy. That's pretty good. You guys, you know, still sharp. Okay, very good. Okay, canonical ensemble, right? In micro-canonical ensemble, constant N, constant V, constant E is the total energy. Canonical ensemble, NVT, constant number of particles, constant temperature, constant volume. What is the characteristic? It is the, okay, partition function. What is the partition function for this?
Sum e to the minus beta.
Yes, e to the minus beta e, right? Canonical, right? Canonical partition function. And what is the actual function? The characteristic state function. This is a free energy, right? F. It's a free energy F, and for MPT as a thermal isobaric, this is a very important ensemble, right? Control pressure, control temperature, or control temperature, control volume, control mu, chemical potential, right? So this is grand canonical ensemble, right? Now, let me ask you, for the MD algorithm, right? You're gonna integrate Newtonian equations of motion, right? Which ensemble MD simulation will get you? Let's check one at a time, right? N, number of particles. It's constant, right? And what about V? Okay, V is, you know, we don't do anything, V is constant. Then, why E?
Because T is change.
T could, right? T could change. T could change. But E, why E is a constant? It's Newtonian. It's Newtonian, right? So the native ensemble for MD is NVE, micro-canonical ensemble, right? So if you don't do any, you know, manipulation of MD simulation, it's going to give you NVE. Now here is a very important tip for you. The very first MD simulation, if you are getting a new system, even when I design a new system, the first simulation I do is NVE simulation. What do I check? What is a part, what do I check? I know atoms are not gonna be lost. I know the volume not gonna change, right? I'm gonna check the total energy, whether it's a constant. Maybe I implemented a new force field. I had a little error there. It's not exactly derivative, you know. Then I'll have to check whether the total energy is conserved. So any new simulation, you should run NVE to check whether the total energy is constant. Okay. I hope you remember this when you do the lab, right? Yes.
Can you run into machine precision?
Absolutely, absolutely. So if I run a really, really long simulation using NVE, the machine, essentially the integration error can essentially build up, and you could increase your total energy in a little bit higher, over, I don't know, 10 billion time step runs. It's absolutely possible. Sometimes when you have to run really, really long simulations like this. For instance, if you want to calculate the diffusivity, right? I don't want to use a thermostat. I just want to run an NVE. I preserve the dynamics. But when you do it really, really long, you could run into the problem. The temperature rises a little bit, right? So at that point, you have to couple a really weak thermostat to suck up that energy produced by the imposition of the integration. Absolutely, this is true. Yeah. All right. How do we control the temperature? A very simple way to control the temperature is this, right? So now, from this native micro-canonical ensemble, we want to produce a canonical ensemble, right? We want to control the T as dictated by you. When you put, oh, my target temperature is 300K, right? How the simulation will do it for you. So what you can do is that, okay, I'm going to calculate the instantaneous temperature, right? Instantaneous temperature, and then I see, oh, is it lower than that or higher than that? And then I'm going to rescale all the velocities according to it, right? Very simple. You know it's going to work. What is the bad thing? The bad thing is that essentially you are scaling the velocity, right? So the statistics is all wrong. Make sense? The statistics is all wrong. So a better way to do that is to sample from a Boltzmann distribution. So at least my distribution is correct. At least my distribution is correct. There's also, even better way is to this is the thermostat, right? So control the temperature. This is essentially obtained by sampling a Boltzmann statistics. Now let's talk about barostat, controlling the pressure, right? We can achieve NP. We can achieve pressure, isopressure, isobaric simulations. So that is very important. For instance, for any experiments, right? Most of the experiments are done at a particular temperature, 1 atm, right? So we have to be able to control the pressure. So the first way to control the pressure is very similar to the temperature control. You calculate the current pressure. What is the instantaneous pressure, right, you have? And now I can see, oh, what is the target? If the target is higher, I'm going to compress it, right? So the compressibility of the system has to be positive. Otherwise, the system is unstable, right? Thermodynamically unstable. Or if the target is low, so I'm going to expand the system, right? So in this way, I will be able to control the pressure. So the way to control the temperature and pressure in these ways destroys the dynamics. Think about MD simulation. The most important thing about MD simulation is follows the Newtonian dynamics, right? It's a continuous trajectory. Anytime you rescale the velocity or resampling the velocity, that knock it, right? So that's bad. A better way is called the Nuzzi-Hoover thermostat and barostat. Basically, they use the extended Hamiltonian method to add another variable to the whole dynamics. So you can preserve some of the dynamics, not the whole dynamics, right? So this is slightly better, right? Okay, force field. Let me see how I do time-wise. Okay. Force fields. So I told you about linear drones. Really, really simple two-body interaction. You can have more sophisticated force field. For instance, you can have an angular bending, right? Angular bending. This is, of course, a three-body interaction. Or torsion, or electrostatic, and usually a classical potential can be written. This usually this is essentially just depends on where the atom is. You could be subject to a electrostatic field, right? Electric field, or this is a pair, 3-body, 4-body, so on and so forth, right? So now you have to realize that every time you throw in another, beyond 2-body interaction, your simulation gonna be significantly slower. Make sense? Right? Because not only you're gonna essentially have to count another loop, but the interaction is way more complicated. Right? The interaction is way more complicated. Particularly when you're talking about calculate the pressure, calculate the viral of a 3-body, 4-body term. It's, the derivation is few pages. Really, really, really complicated, right? Now, this type of potential is very similar. Let's look at the form, right? Let's say here is just a spring, right? Hooky spring, bound stretching off the equilibrium bound length, then you give it an energy penalty. Or the angular bending, angular spring, same thing, right? Torsional term, electrostatic, van der Waals interaction, right? This is almost a universal force field used in the biology community. There are a bunch of different flavors, charm, and all kinds of force field. Now, a very important point here is that this bound, if you write in the case of a linear spring, never break. Make sense? They never break. So, in writing this total energy, you have to separate the atoms into essentially bounded pairs and non-bounded pair. Make sense? All right? So you have to tell, okay, this is a linear spring. Now you're going to use linear spring. Make sense? So that bond will never break. You don't have chemical reaction. Make sense? Right? As opposed to van der Waals interaction, it doesn't matter. I never said this atom is a van der Waals, right? It depends on whether we're close. Then there's a bonding, right? Next time, I'm not, right? As opposed to, okay, this is the angle. I have to maintain 190 degrees, so on and so forth, right? So this is bounded interaction used extensively in drug discoveries and so on, but it has its inherent limitations. Yes?
So in this case, we're only talking about like all atom solutions, right? Because
yes, absolutely.
I know they have like mixed quantum and molecular mechanics. With those, you can break bonds.
Absolutely, absolutely. There are other force fields you can see that will be able to treat this. Not using. There are interactions beyond this bonded interaction to study chemical reactions in EMD. Yeah, absolutely. Those interactions called reactive force field, right? Bond order potentials, and so there's actually one example here. Okay, so for these non-bonded interactions, we call it reactive force field. You have many flavors. One flavor is called embedded atom method, EAM potential. Essentially the formula are almost the same as the density functional approximation. Depends on the environment. For instance, right? So the local electron density, right? All my neighbors upon me, that will affect my interaction. That will affect my potential. So basically, this rho is the electron density on this atom, right? So that depends on if I'm surrounded or I don't have many neighbors like on the surface, my interaction is different. So this is intrinsically, EM potential is intrinsically a many-body potential. And then you have the pair form. EM potential is used extensively in metal systems, alloys, or single crystal metals or metallic glass, so on and so forth, right? So this, if you're dealing with mechanical properties of metals, EM potential is sort of your, default choice, EM potential. The other type of flavor is called bond order potential. So what is bond order? Bond order, by definition, essentially number of chemical bond, right? So bond order depends on, also, essentially depends on the neighbor's distance and the chemical species between you and me, and they calculate a particular bond order. And the bond order will play a role here. So this is intrinsically a many-body term. So Brenner and Tursuff and Abel, they sort of developed the first set of carbon-hydrogen potential, very, very popular. So Brenner is actually my postdoc advisor. So he invented this so-called Ribot potential. And anybody heard about Reax force field? So this is Bill Goddard in Caltech. He has like an army of researchers, modelers working for him. He has this Reax, probably the most popular reactive bond order potential out there. So it's also very similar. So that the Reax can, model all kinds of chemical reactions, same as Ribot. Yeah. Okay. Now I'm going to give you a few examples. So mostly my own research, because it's, I have to be able to assemble this presentation, quickly. I don't want to read new papers. I know what I'm doing. Before I go sort of tell you about these specific examples, I want to say MD simulation can be used sort of roughly two ways. One is in equilibrium, the other is in far from equilibrium. Okay, in equilibrium, you can see, you already know all these ensembles, right? So we could use MD simulations to study, say, copper. I can calculate the equations of state at this temperature, melting point. Well, melting point is tricky, right? But you can, right? You can calculate all the equilibrium properties. Lattice constant, what is the modulus, right? What is the vacancy formation energy? All these you can calculate. Or another big category that probably MD simulation is primarily applied to is non-equilibrium or far from equilibrium simulations. For instance, shock, right? Shock is in fact one of the first few MD simulations done. Right? So basically the process nowhere near equilibrium, but you can still trust the complete trajectory because of the Newtonian dynamics. Make sense? So the Newtonian dynamics is, I can stress again and again, because if you have atoms with that force field, right, interact like that, it will be like that. It will follow exactly the same trajectory. Yes?
So for materials, would you be able to calculate the entire stress strain plot?
Absolutely. You will have the chance to do a nanotension test of a single crystal nanowire. You will be able to plot the stress strain curve. You can. Absolutely. We probably emailed each other last night, right? To set this up. Because I spent like half of my research life on fracture, so All right. Okay, first example. This is a deposition simulation, right? So there are atoms coming down. There are 3 species of atoms comes down, and then it will form crystal island. This is a island growth. You will see crystals forming, grows up, right? Okay. Oops. Oh, sorry. Oh, actually it works. Okay. Whew. All right, good. I thought it's not copied over. So now nucleation grows. Anybody guess what kind of crystal structure this is? Clue, 3 species. It's hard to just look at it, but so here, what we try to see is once you have this growth, what kind of defects the film has, right? What kind of defect this film has. And we can manipulate the substrate to see if there's a way we can lower the amount of defects on it, right? This particular film is a perovskite structure, right? Also very important for superconductors. And recently it is very, very popular for solar, essentially PV, photovoltaic. This organic perovskite is, has such a high efficiency. I don't know, 20%, something like that. The problem is that they don't last very long, and they're really cheap to make. On campus there are a few groups working on it. That's why, including Professor Tongming Lu, Go-Jing Wang. So that's why I sort of started some simulation on this. And here is a top view of the same film, and you can't see much over here, right? But we can do this very important analysis. We can do analysis. That's why we have to spend so much time, writing analysis code and so on. We can actually figure out the misfit dislocation. All these lines are misfit dislocations, right? So we can calculate the dislocation density for different substrate. Not only that, those are misfit dislocations, right? There are 2 dislocations, are threading dislocation. One is right here, the other is right here. So basically, the misfit dislocation, right? If this is the substrate, right? Misfit dislocation is parallel to the substrate, and the threading dislocations are perpendicular. The one parallel to the substrate is not that harmful. Make sense? But the threading ones, then it grows throughout the thickness, right? So we will be able to get those atomic level insights into the problem, right? Second example, this is a very messy situation called stress corrosion cracking. Anybody heard about this term? Stress corrosion cracking. Very good, right? Very good. So the first time people realized there is so-called the stress corrosion cracking is in India in the colonial era, that the British, the shells and so on, they crack during the summer. This is because of the amount, the environment. There's so much manures and so on. They decompose. There are a huge amount of methane ammonia in the environment, and the ammonia together with the residual stress of the shell of the metal create the crack. Right, so they basically destroyed the shells, and later on people find out, oh, they have to anneal the metals first to anneal out the stress. So in this case, you have to have stress, you have to have chemicals to be able to grow the crack. Right, so this is called stress corrosion cracking. Not only in metals, in glass, you have the same situation as well. So for instance, Corning everyone knows Corning, right? So I did a sabbatical there 3-4 years ago, and there's a guy who talked, essentially talked me into this stress corrosion cracking. Is basically they face a problem. They use the so-called chemical strengthening, right? Chemical strengthening to increase the crack, sort of scratch resistance and so on, right? Our iPhone is all chemical strengthened, right? You have this big part, big ions sticking on the surface to create this compressive stress so that it will prevent the crack opening, right? Now they want to use the same thing on borosilicate glass for essentially vials, right? The vials will hold the little chemicals. The chemicals could last, I don't know, 5 to 10 years and so on, right? However, the problem is that the chemical strengthening create a stress field. So they are so worried that 5-10 years down the road, the combination of whatever, you have to have some solvent, right? The solvent and the stress, they're gonna create a crack, and they're gonna, crack, essentially fracture the vial, right? So they want to understand the stress corrosion cracking mechanism. Okay, so these are the background. So what you see here is yeah, please.
Do you also do this from like stainless steel?
Absolutely.
Exposed to salt water?
So stainless steel. So basically we want to separate the question of just corrosion or it's a stress corrosion cracking, right? So you could have just chemical attacking, right? But with stress, the crack grows way faster, right? So it's not just corrosion. Yeah. So in a way, in a more physics point of view, is that it is the stress lowers the reaction barrier for the bond breaking, right? So that's the key of this chemomechanical coupling, right there.
And Jerry Kornowski was telling me about they built some mall out in New York somewhere here with the rebar in the concrete.
Okay.
It wasn't covered with something to protect it. The solvent and all the water that's in the concrete.
Okay.
It destroyed the
possibly. Yeah. It has to be chemical and mechanical together. Yeah. But usually in a tension, I mean, the rebar probably in, I don't know. I don't know. Yeah. All right, let's look at the animation, but basically these are chemicals. Those chemicals likes the, remember it's a red atom, right? So this is a binary glass, it likes the red atom, and it wants to plug it out. So selective dissolution. Make sense? Right? It want to dissolve the red atom into it. Of course, that is essentially the chemical reaction we're after. So now there's a stress applied. You can see the corrosives are, huddling around this red atom and weakening the glass, and the crack will start slowly grow, right? Slowly grow. So there is debate in the community for the past 50, 60 years. I mean, not a debate anymore because the people proposing those formulas are all dead or near. But we still don't know whether it's exponential form or power law. This all. So there are still very important questions left to be answered. So this is another example of nanoparse carbon. So in this case, we try to let the atoms, right? This is actually, similar to a reactive bond order potential. Then the carbon atoms, very, very high temperature, and then when we cool it down, they start to form this network. It forms this nanoparse carbon. You can see right here. Okay. So very complex three-dimensional porous structure, nanoporous carbon. Right? And we can, in fact, compare to the experiments. So you can see all the, in terms of S of Q, right? Essentially, you can think of this X-ray diffraction pattern. It matches very well. Now, there's another simulation technique called Monte Carlo, especially hybrid Monte Carlo, reverse Monte Carlo, sorry. Reverse Monte Carlo. So you could take the S of Q, right? And then you can come up with a structure to produce exactly the same S of Q. This MD simulation is not. The S of Q is not part of the input, right? Okay, so that comes to the summary. So let's, rewind the whole crash course on MD. The flow chart, right? Think about how do you accomplish MD simulation? I don't know, you. So what is a flow chart? First you do what?
It's like the chef.
Well, not the chef, but I like the chef. But so the MD, you start with what? Atoms, and you know the positions and velocity and the force, and then what do? You get you integrate the equation of motion, right? And you do it again and again, basically, right? So this is the flow chart. Important algorithm. You name one.
Verlet algorithm.
Verlet neighbor list. Yeah, okay. Verlet velocity is for the integration. Okay, you know that? That's very good. Okay, so I kind of skipped the integration part. It's kind of boring, but very good. You.
Yeah, so the Verlet list would link cell, like you can use a linked list to hold all of the particle positions.
Yes, so you essentially, kind of you kind of store the knowledge that the atoms are nearby by this link cell. You know the cell's neighbor right away because they are grids, right? So then it will speed up the simulation from n square scaling to n, order n. Very good. What else? You.
Have we divvied up the CPU part yet?
The spatial decomposition using the parallel algorithm, right? Using many CPUs to crunch the same number, basically, right? For the same simulation system. Yes?
Using locality, so only considering atoms closest to the atom you're looking at?
Yes, very good. So that is kind of close to the neighbor list, right? But you have this cutoff and so on. Yes. Probably one more. One more we discussed. We don't want the surface, so we have this little trick. Periodic condition. Excellent. Very good. Okay. Important algorithm, various ensembles. We have the micro-canonical ensemble. We have the canonical, grand canonical, isothermal, isobaric, and we can control the pressure and temperature. And the native one. What is the native ensemble? Micro-canonical. And different force field, and okay, MD is very versatile, right? Okay, so we can take a break, and now I upload 2 files into the Dropbox. So it's about 100 megabytes-ish. So before the break, you can start downloading. I would, you guys can work in pairs or work on your own, that's fine.
I noticed, so I looked at it and I noticed that it looks like it's Windows.
Yes, it's only Windows.
Yeah, so if people have a Mac, they should partner up with somebody who has a Windows machine. So
please, yes. Now, if you have Mac, you can possibly download the, maybe there is a workaround, but the version I uploaded on Dropbox is only Windows.
And when I unpack it, copy it someplace and unpack it, but first unpack it in the Dropbox folder. That's how it works.
often is called melt.in, right here. Melt.in. So let me see if I can open with a notepad or something. Or WordPad. Usually I like WordPad better. It breaks down the line break more correctly. All right. So here is the syntax for the MD engine. The MD engine here is called LAMPS. LAMPS is the almost, I don't know, overwhelming sort of number one MD of software of choice. So over the years, it becomes better and better. So I'll give you a little story. My PhD advisor wrote himself a MD package, right? So of course I have to use it, right? So but I feel like it's slower than LAMPS. So essentially I just look at the LAMPS engine, I look at my advisor's engine. Oh, here I can speed up a little bit. So then at the end of the day, it is only like 20% slower. So then after my PhD, I started to use exclusively on LAMPS because it's very customizable. It is written in C++, so it's not Fortran, but it's it's a little higher level, so that you can do all these these inheritance and so on. Data structure is it's the best data structure, very convenient, right? Another point I want to make is this: MD is Newtonian dynamics. You're supposed to understand every line of it. Make sense, right? Not like DFT. I bet nobody using DFT package understand the line. They don't have the software. I mean, many don't have the source code, right? And it was, even this, the open source one, it has, I don't know, millions of lines, right? So, but MD, you should be able to understand every single line of it, right? So I always tell my student that if you run into a problem, why it behaves like this, go find it out. You will find out, right? You will find out. All right, come back to the code. This is the, oh yes. Let me zoom in here. Yep. Now the units is Lennard-Jones. So spend a few minutes on this. Lennard-Jones units means everything is in internal unit. Internal unit means that every length is one. One what? We're gonna figure out later. For instance, if the crystal, right? Let's say this is FCC crystal. If the crystal I'm simulating is copper, then I will take the copper lattice constant and map it out to what this one means. Make sense, right? What about the energy? The energy I will get from the melting point of this crystal. Make sense? So everything I can map out. The copper mass will be the one mass unit in the Lennard-Jones. Everything is reduced unit. This is like your CGS. Make sense? You like another set of unit, for certain things, right? If you're dealing with, atomic size, you always use, AMU, right? EVs, angstrom, so on and so forth. You don't want to drag, 10 to the minus 9 all the time, right? So this is internal unit, Lennard-Jones. Atomic style, atomic, so no molecules here, right? There's no bounded, remember the unbreakable bond, right? That is for molecule, in this case, atomic. Lattice, FCC. Everybody knows what FCC is? All right, so you guys all know a little bit about crystallography, right? BCC, FCC, simple cubics, and so on. Excellent, right? So then you will have a little fun in, later, all right? Okay, so lattice FCC 0.8442. The 0.8442 is the number density of the lattice you're gonna create, right? So how many atoms in a one FCC unit cell? 4, excellent, right? So it will be 4A cubed equals 0.8442. So you will be able to know what A is, Okay? Region. Box. The region's name is called box. The type of region is called block. Block is just a rectangular block. From to in 3 directions. So from 0 to 10, 0 to 10 to 0 to 10. Right? So this is a 10 by 10 by 10 FCC lattice it's gonna create later, right? But this is just a region. And we're gonna create box, one box. That means there's only one atomic species in the system, and we're gonna use box that you just defined, region, as the simulation box, right? So now we have the simulation box. Now you know the periodic condition, right? So if it is over here, I'm gonna minus it over here to calculate the minimum distance, okay? Very important. And also the simulation box is orthogonal. Orthogonal. It could be not orthogonal, but the calculation will be more complicated, right? Imagine that you have a very slanted angle, right, for the simulation box. Let's go this way, right? Think about, you want to get all the neighbors, it's not easy. Make sense, right? So you want to be a orthogonal box, easier to do parallelization and so on. The default ones, you always use orthogonal. But in certain phase transformations, like for instance silica, you want to have the flexibility that the box can tilt. Okay, that's another story, right? Create atoms, one box. Among the whole region, among the whole simulation box, you're gonna create this FCC lattice with that number density, right? So how many atoms I'm creating? There'll be 10 by 10 by 10 unit cells. Each unit cell has 4 atoms. There'll be 4,000 atoms, okay? Mass 1. Type 1 is 1, okay? 1 what? 1 internal unit. 1 internal unit. You can map it out later, okay? You can map it out later. Velocity, all create. So this all is a group identity. All is a default, all the atom, right? Very readable. Create means that you're just gonna initialize a random distribution of velocity with a target temperature of 0.3. 0.3 what? 0.3, your internal energy unit over Boltzmann constant. If your internal energy unit is 1 eV, that means right here is about 3,000, 4,000 Kelvin, right? 1 eV is like 11,000 Kelvin, right? 87287. It's a random number seed, right? Random number generator seed. Okay, now let's look at, this is the pair. Let's look at this. Let's look at this first. I commented out, but you can comment it back. It doesn't matter. Let's comment it back. And then you get rid of this 3. Oops. Yes. Right. Now, pair style. This is a force field. Pair style. This is Lennard-Jones cut. This is a Lennard-Jones potential for epsilon sigma over r to the 12th minus sigma over r to the 6th, right? 12/6 potential. 2.5 is the cutoff. At particular 2.5, anything beyond 2.5, no interaction. Okay? Why it is called the Lennard-Jones cut is because basically at 2.5, it still has a little bit value. Make sense? But outside, I will just set it to 0. Very importantly, here you have the pair modify shift. Yes. What does it mean? I'm going to shift the potential up so that at the cutoff, the energy is continuous. Make sense? Otherwise, I'm in and out. I will have a jump in potential energy. I don't want that. But the jump in potential energy, the discontinuity, will not change the dynamics whatsoever because force will not be affected at all. Make sense? Right? The force will not be affected. So this is Lennard-Jones cut. 2.5 is the cutoff, and this is a Lennard-Jones coefficient species 1. Species 1. The energy is 1. The epsilon is 1, and the sigma is 1. and then the cutoff is still 2.5. So essentially, the bonding energy is 1. And the sigma is 1. That means the equilibrium distance is around 1. It's 2 to the power of 1/6, right? You can do the derivative of 12/6. So basically, it is 1.12 something sigma, right? So the atoms will equilibrate around, a little over 1, right? That is your equilibrium distance. This set up the force field, okay? This set up the force field. Now we have neighbor 0.3 bin. Bin means link cell. Bin means link cell. So that you are going to use link cell. And what this 0.3 means? 0.3 means that the extra skin layer for your neighbor list. Remember, right? You're going to hold a little bit more atoms around the neighbor list so that I don't need to update the neighbor list that often. All right? So that is neighbor, and you update every, you don't delay, and you don't check. And fix 1 or NVE. This is the ensemble setting. So that basically 1 is the fixed number. You can unfix, like the name of this fix, right? All the atoms, and NVE, this MD will not change, will not do any manipulation. Make sense? Will not do any manipulation. So that it's gonna conserve the total energy. And dump here is, dump ID is the name of this dump, and all the atoms, and dump every 20 time step, and it's gonna dump into a file called dump.melt. And the thermal 10, that means every 10 time step, it's gonna give me the temperature, the pressure, these microscopic thermodynamic variables, and you're gonna run for 250 time steps. Okay, so now let's look at it, right? Basically, it creates a temperature, and then the system relax under NDE. All right. So what you can imagine, the total energy should not change. So the thermal energy gonna dump into the potential energy. The potential energy is going to rise. Make sense? Right? So you're gonna essentially, if you put 0.3, that means your temperature is actually pretty low, right? Do you think it will melt? What is the average? What is the atomization energy for this system? Anybody knows? Anybody familiar with atomization energy? So how much energy I'm gonna break the whole thing, obliterate every single atom into isolated atom, right? This is FCC, right? I'm gonna break it apart. How much energy I have to dump per atom for the system? How many neighbors per atom for this FCC? Anybody remembers? No. Nearest neighbor. FCC has 12 nearest neighbor. 12 nearest neighbor, right? So at least you have to pump. Basically, if we're just looking at nearest neighbors, right? Every atom on average has 6 nearest bond. Make sense? You have to divide it by 2 because every bond is held by 2 atoms, right? You at least need 6 energy unit to break it apart because it's 2.5. You hold way more nearest neighbors, right? Essentially you need, I don't know, 7. You can actually check the log file later, right? Maybe 7 energy units to completely break it apart. So you give a temperature of 0.3, it's like nothing. Make sense? It will not break, right? So let's check it. Okay. So now let's use this. I'm going to save it, and I'm going to run it now, right? So we already know the syntax. We're going to run it. There's a GUI here. You double click, and you say no to the search, and you can run the melt.in, right? So you launch it. Now you run the simulation first. It's going to be really quick. So now once it's not great, you can click run Ovito. This is the visualizer. This is another open source software we use like daily. Okay, now we have Ovito. We can open file. Okay, you might want to do the same thing now, right? Just run it, and then you're gonna. I usually do this, right? You order it according to the date modified, so the new file is always on top, right? I don't have to search for it, right? So dump.melt is the file I want to open. Right now I have the atoms.
Sorry, that
yeah.
we just opened this was generated when we did the.
So that was generated when you run simulation. Then you run Ovito. Yep. And then you open it up, dump. Now you see the atoms a little bigger than I preferred, right? So I will click particle type, and I will change it to, I don't know, 0.3, right? Maybe 0.4, right? So now you see this is your FCC crystal. A trick, so here you click this quadrant region, and you can click here. It would kind of make it nicer, nice and big, right? You can rotate, you can zoom in and out. I think it's control. Not control. Okay. At least you can use this, right? Right. Now here, because this is 250 time steps, right? We can watch the animation. So watch this. Click dump, and then there is a file contains time series. Click that. You can see it loads up 12 frames. Okay. Now you can play it. Can you see that? Basically, the system kind of vibrated a little bit, did not melt, right? Did not melt, right? Right? Okay. Now, at the same time, I do want you to open this. Go to the folder, and I want you to look at this file, log.lamps. Okay, log.lamps. I want you to every time watch the animation, but I also want you to see this data, right? I want you to be able to sort of appreciate the data. So we're going to open up with WordPad, log.lamps. This is a spill out, right? This is spill out. So lattice, and it will tell you, okay, lattice spacing is 1.67. This is your A, lattice constant, calculated from the number density, so on and so forth. There's one processor, created 4,000 atoms, right? It has everything here, right? Now, look at this. This is very important, right? Edge.
I want to blow it up a little bit.
Oh, I'm sorry. Right? So what I'm saying is that it has all these messages, right? So it's one CPU. If you're running parallel, it will be like 2 by 2 by 2, and this is the box size. This is created 4,000 atoms, right? And then look at this. This is an important message out. Look at this. Step, time step, temperature, the pairwise interaction. This is your potential energy because you only have pairwise interaction. This is molecular interaction, nothing, right? There's nothing here. This is total energy. And this is pressure, right? So now you see here, for some reason it's, enter a new line, but this is time step, temperature, potential energy, total energy. This is pressure, okay? Now you see, what is the first thing I should look at it? What is the first thing I should look at it? Total energy, right? I have to check. I have to do the sanity check to see my total energy, whether it's conserved or not. Many of the, I don't know, even PhD students working on MD, they kind of forget that. It's very, very bad, right? I hope you guys, maybe one day working on MD, total energy, NVE simulation first, okay? All right, total energy, minus 5.88294. Okay, right? Look at this. Not too bad, right? Not too bad. I welcome you to change the time step. Okay, the time step is not written there. Then you just add it. Okay, let me do that because it's from a certain year you don't need to write time step, and then everybody forgot. So here, right? Just write time step 0.05. This is the default, okay? All right, now let's look at here, right? So now you can see at the beginning, you have 0.3 of temperature, and then later on, you see that it stabilizes at about 0.15, right? So all the kinetic energy transfer to the potential energy, right? Your potential energy increases, right? You kind of have these lattice distortions and so on, right? So the total energy stays the same, right? Any questions here? All right, okay, yes?
So in your simulation, you said the energy should be a constant. So why in the results the energy will change?
No. The total energy is a constant. Look at this. Yeah. 0.58828, right? Yeah, it didn't change.
But if you set it to be a constant, why do you say you need to check it's a constant?
It's because the time step I might set it wrong, or the force field I just implemented may be wrong. So this is the sanity check. Every time I have a new system, I have to check. You see what I'm saying? This is like your, if you're working with, TEM, you probably pop in a silicon sample or something to check, whether you have the right crystal structure, right? This is a sanity check. You have to do this. Yeah. Although it's NVE, but if your time step is set wrong, go ahead and do it. You will see the total energy drift.
So what does the time step do?
So basically, you want the highest, the largest time step that will not mess up with the integration, so that you can achieve, say, 1 nanosecond in less amount of time step. Make sense, right? So you don't want to, the time step is 1 femtosecond. Okay, 1 femtosecond is okay, right? This is like a typical time step. You don't want, like 0.001 femtosecond, because you're gonna do 1,000 times, longer, and then you have the same results, right? So you want to have as large a time step as possible. Yep. All right. Now, just go ahead and change the melt dot in, and what I will do is I will just create 3, right? I will create a really large high temperature, and I'm going to run again. Oh, I'm sorry. Yeah. So I go to melt.in, and I change the velocity all create to be 3.0. So it's a way higher kinetic energy, right? And I will see whether I can destroy that FCC crystal. Okay.
You added a time step line.
Yes. That is. Yes, it's above the fix.
Does it need to be there?
It's.
The order matter?
Yes. As long as it's above run, I don't think it matters. Yep. So run is where it starts to run. Yep. Okay. Now, this is the part. Okay, let me do this. So I also share with you a Google slide, right? In that MD summer school doc, you can check the short URL. So I will jot down some notes so that I will not forget. So here, add time step 0.05, change that. Okay, I hope you will have it. You can open up a separate windows, and then change 0.3 to 3.0 in velocity create. Right, so that's the two things I did. All right, now I'm gonna go back and run the simulation again. I'm gonna run Ovito again. I'm gonna open up here. And I'm gonna click here, so I will have the time series. See, I melt right away. I destroyed this FCC crystal right away. Okay? Make sense? Right. So,
and then you might fine-tune it. You don't want 3, you want maybe 1.
Absolutely. So think about it. This is the part that I, you know, one question I have for you is, how do you get the melting point?
I'd say now pick something low, greater than what you originally had.
Yeah.
And then if it doesn't melt, pick something higher.
Right. So it's like a recursive process. But this is complicated, right? You probably, I don't know. also, it is not that it melt at 3, right? You know, if you give it a temperature, right? In NVE, you know, there's like, you know, the temperature dump into the potential energy, right? So it's better if we choose maybe a canonical ensemble will be better. Make sense, right? And instead of trying this particular temperature, I make, you know, do a heating process, and we'll see exactly where the potential energy will go up. You will be able to see it. Make sense, right? So, yeah.
As you change the temperature, it is affecting all the molecules at the same time.
Yes. Yes, this is global.
Okay.
Yep.
You don't have to worry about like a transition.
No. Right. Yep. So let's do this. Let's modify it a little bit more, right? So what I'm going to do is this, right? I'm going to change this. I'm going to change back the 0.3. Okay, I'm going to change back to 0.3. Now, instead of an NVE, I'm going to change to an NVT. Okay, how do I do that? I will comment this off. Okay, go with me. You know, do it at the same time. You know, if you just watch, maybe, you know, you'll not get enough. All right. So now I'm going to write like this: 1 of NVT, temperature 0.3 to 3, 1.0. What this means is I'm going to use a Newton Hoover thermostat. I'm going to heat up from 0.3 to 3 with a coupling strength to that thermostat. Time scale is 1, right? So the higher the last number it is, the weaker the thermostat is. The weaker the thermostat means that, you know, it's not coupled very tightly, so the actual temperature can be way off. Make sense, right? So 1 is a kind of a default one I generally use. So in this way, it's going to heat up from 0.3 to 3. Hopefully, I will get a better melting point, right? And I cannot do 250 time step now. This is too short. I'm going to do, I don't know, maybe 10,000. All right, I'm going to try 10,000. I'm going to save it. Right. So let me update the other side. So now change back to 0.3 as velocity create, and remove fix NVE, add fix NVT, right? So the particular sentence, I'm going to copy it over right here so that you will have it right over here, right? Okay. Now I'm gonna run it. $10,000 time step will take, I don't know, 40 times longer. You know, gonna wait a little bit. So if you have any questions, you can. Okay, finished. Now we can run the simulation. Oh, I'm sorry. I should run Ovito. Definitely not the first time. Yes.
Or you can change the radius. This time change the radius of your atoms.
Okay. How do I change the radius of the atom? Yes. In the over here, right? What set the radius of the atom is right here.
Patient needs the visualization.
Oh, okay.
Yeah, I
all right.
created the
Yes.
animation.
Yeah. Hold on a sec. Okay. Run Ovito, and we're gonna open up the file. Over here, atom type, and then you can put 0.4 right here. Got it?
Yeah.
Yep. Then let's watch the animation. It's heating up, heating up. Please melt. Okay, that's pretty much melt. Make sense?
That's cool. Does it read off the temperature somewhere in there?
Of course. Now let's not satisfied by animation, right? I kind of want you to have that sentiment, right? Now let's look at the log file. Okay, there's no reload. I have to open up again. Okay, now this is very important. That's why I ask my students, right? Every time, not only look at the animation, but also look at the log file, right? Here, we open it up. Okay, this is the log file, right? Now, you will be able to, I'm gonna copy all the, so if you have Sigwin, you can do it using my favorite plotter is XM Grace. Anybody use XM Grace? No? Oh yes! All right. Finally, many people use GNU plots, right? That's equally useful, right? Okay, I'm gonna copy it over. I'm gonna open up my least favorite plotter, but fortunately and unfortunately, it's available in every Windows machine. So, what you can do? All right. Okay, so I can text to column and delimitate space. Finish. All right. Now we have the temperature and potential energy. Hopefully, we'll see a jump. Right? So here and here, temperature, potential energy. We can plot, insert a scattered plot. All right. So that's the reason I don't like it that much, right? Because you can't zoom in, right? But you can roughly see where it is, right? Do you see? Right? It's right here, right? Is this the melting point? Is this the melting point? So this is not the melting point because it depends on how quickly I hit it, right? So in MD simulation, if I want to do a quick estimate, I would use this, right? I would use, I don't know, maybe 1 million time step, right? If I want to know exactly what the melting point is, how should I do it?
So is there history?
Yeah.
Is there?
If you cool it down, absolutely, yeah. But the hysteresis, there's also controlled by the nucleation growth on the freezing side, right? That's even more daunting. The heating is supposed to, be controlled by kinetics less, but you still have it, right? So if you want to have the accurate melting point, you should create a liquid-solid coexisting situation. Make sense? Right? Now you will go to the equilibrium simulation. You will get an accurate number out instead of this non-equilibrium heating. Right? Think about MD simulation. Everything is really, really fast. You're talking about nanosecond, right? Thousands degrees in 1 nanosecond, or even less, right? So it's extremely fast heating. So everything you have to think about it, right? You have to think about it. That's why if you want to have the accurate melting point, you have to simulate the equilibrium, liquid-solid coexisting, right? Really, really control. At that time, basically what you can think of is that I'm going to have a flat, solid liquid interface. I'm going to provide a good gas. I'm going to see whether the solid grow or solid shrink. Then you change. Now you're going to have a very accurate number. Yes?
Do you just take the initial positions from this run that you just did?
You could. So what I can do is, what you can do is you create a solid and you freeze them. You don't let them move. Let it the other half to be liquid, and then and then you subject to a new temperature. Yep. So all these tricks you can play. Yep. Okay, now look at, you will be able to use Ovito to look at animation, right? And also look at the log.lamps file. You will be able to plot these very important characteristics, temperature versus potential energy, and so on, right? Okay, now I want you to, what else I want you to do? So let's go back. So I want you to modify the in-dot melt. This is something fun you can play, right? I want you to create a system that with a flat substrate, right? The substrate is frozen, right? And now you have a ball that is flying to the flat substrate. Make sense? All right? Very simple. Very simple. What you need to do is, this is almost like you have to do a little research yourself, okay? I'm not going to provide everything, right? So this is actually what you do, right? I will provide a few command you look up online, all right? So think about it. I want you to create a slab, right? So you already know how to create a slab, do you? Right? Region, block, right? You know where it is. And now I will give you that the region also can define a spherical region. And you basically create atoms in that spherical region to create the ball. Right? Then you give those ball a velocity. That's it. Make sense? So what you need to do is to check the region sphere. Okay? So how do you get that? You just type region sphere. Oh, see? Even Google knows I'm talking about lamps, right? All right. Google will make us less smart, right? Okay, so see, now this is how you do it, right? You can do, region and your favorite ID, I don't know, right? And sphere, the center, the radius, and usually side in, right? But you try side out, you'll see arrows, then you try again, right? Now, if you don't put anything, it is the unit of lattice. So 5 unit cell long, as radius. Make sense? Right? Now you create the region. This is how you essentially check the syntax, do it over there. What else you need to do? Let me go back to here, right? Region sphere, right? So think about you create a sphere, create atoms in it, right? And then you have to group it. Group means that you can essentially group certain amount of atoms into a group based on region, right? So basically it's here too, right? Group, group lengths, see. I know why, because I already logged in, so it knows all my search history. All right, so group, so look at this, right? Group, you can call it sphere, region, whatever region. Make sense? Right? It's very straightforward. And once you know group, then you can velocity. You use velocity create already, right? Now the next one will be velocity set. All right? Look at this. So basically, this is velocity create, and you can set a particular velocity, right? So now you want the ball to plunge into the plate, or use two balls. Okay, that doesn't matter, right? Just create two balls, let them smash. See what happens. All right?
It looks like you can set a vector too.
Absolutely. This is 3 vectors. If you don't want to set the other velocity, put now. Very flexible. Right? So now, velocity set, right? Okay, your little task. Let's see who can get the first 2 ball pounding each other. Your professor gonna give you an award. If you have any questions, raise your hand. Don't be shy to. Yes.
The dimensions of this too.
Yeah. Go.
10, but it's 2.
No. This is too much. So basically, go back.
Okay.
You can't go back to yes. So you can't change this. This is your simulation box. You still want the big simulation box to have 2 spheres.
Oh.
Make sense? So you should create another region.
Okay.
Leave that box alone.
Okay.
So do not change the box 0, 10, 0, 10, 0, 10. That's your simulation box. You still need a big simulation box for the balls to play, right?
But we make 2 new regions.
Exactly. You make 2 new regions.
Yeah, the lamp expert.
Oh.
We have an experienced user here.
I like the color. Wow. Let's see who can get the ball smashing first. Yeah, that's fine too. Yeah, velocity is set.
Yeah, I want to see how.
Yeah.
Because I have it on all right now.
What's that?
I have it on all right now. I have the velocity.
Yes, so you have to create a new group.
Ones for each of my items.
So here, let's say.
So I have my.
Okay.
This is what I'm working on.
Oh, you're gonna.
I haven't visualized it yet.
You have to be ball 1 and ball 2. Otherwise, this is you know.
Oh, you're right. Yeah, they know the same thing.
Yeah. So now you should, you know, this should not, so there will be 1 and ball 1 and ball 2. You see what I'm saying? So otherwise it will create the whole thing. So here it's create atoms 1 box. It already created all the atoms. So to change this to ball 1. So another tip for you, right? You want to change LAMP's code 1 line at a time. And you save it, you run it to see whether that's what you want. Make sense? If you change like 20 lines and you got like nothing, okay, what to do next, right? So incremental, right? Then run it again, you will see only 1 ball.
0, 5, 5, right? That'll put it.
Yes.
Would that put it on the edge of a box?
Yes, that's fine. Okay. That's okay.
And
yep. You select the radius.
And
3. Let's say 3. Yeah. Yep. Remember, you're gonna get rid of the create atoms 1 box. Because don't delete it.
Comment.
Just comment it off. Don't delete the sentence, right? Comment it off using the punch, right? You shouldn't have this create atoms 1 box, right? That will create all the atoms there, right? You should change it to. Anybody already create a ball already? Raise your hand. Okay, getting there.
It takes my mind like 10 minutes to load.
Oh, really?
So is this like the right idea? Or
let's see. Yes, region, ball 1, ball 2, excellent. And then 0, 0, 0, 5, that's fine. Box, well, right? don't use side out. Okay. That will create a hole. Yes, or you don't say it. Yeah.
Oh, you can. Okay.
Yeah, you put 3 because this is 0 to 10.
Okay, yeah, that makes sense.
You know.
3. Yeah. 2.5.
That's fine. And then the other one could be 555 or 500 on the same line. You want them to smash against each other, right?
Right.
You're always gonna load the
something like that.
Or 500. Otherwise, when you create the velocity, you have to point out the right direction.
That.
Yep.
Okay.
And then
5 equals 5.
That's fine. And now you create the atoms. Oh, you get rid of that sentence. Don't. So create. Oh, here, right? So you should create atoms 1, region ball 1, 1 region ball 2. No.
Oh, not there.
Not there.
I see.
Right here.
Okay.
That was what I was saying. You already have that. You already have these.
Yeah. Region. 1, yes. 1, yes. And then region.
And then whatever the region of the sphere is?
Exactly. Ball 1, ball 2. Yep. And then stop, run it.
Okay. Thank you.